My name is Rohit Agarwal. I work as a software engineer at Databricks. I also contribute to Envoy. Today, we'll be talking about access logging and the impact of access logging on throughput, impact on cost, and we'll see some of the ways on how which we can increase the throughput and we can reduce the cost. So just to give a very high level overview of how envoys are used at Databricks, we use Envoy extensively. We have data planes where we use Envoy as an egress proxy for MTLS and a lot of other use cases. We have millions of these data planes across all three clouds, AWS, Azure, and GCP. We also use Envoys as the API gateway, as a main ingress proxy for all the incoming traffic in our control plane. We have two-layer or two-tier architecture where we have Envoy as an L1 proxy and an L2 proxy. We handle all sort of protocols, HTTP, MySQL, Postgres, through these envoys. We do have a lot of high throughput and cost sensitive use cases for which the throughput becomes important. That's why we have to think about how much we are logging and how we are logging. So just to give one of the access patterns, we have data planes, we have some services or workloads in these data planes, which are talking to egress envoy, and then we are doing MTLS to control plane. And then we have a API gateway or an ingress proxy, which is doing a lot of stuff. It's doing external authorization, rate limiting. We have retries and everything built into this envoy. And then finally forwarding requests to the control plane services. Now, if I look at the logs, we do have multiple layer of access logs happening both at the egress side as well as at the ingress side to do a end-to-end view of what happened with the request. If I double click on the Ingress Envoy, the architecture is a little bit more complicated than this, but this is a very high level overview. We have multiple filter chains for different use cases. Depending on what SNI the request comes from, we pick one of the filter chains. But this is a traditional setup that all the filter chains, especially the HTTP filter chains, would have. We have many filters, RBAC, header to metadata, x.z, rate limiting, xproc. Many of these filters are emitting filter state and dynamic metadata. For example, xproc would emit dynamic metadata on what happens when the request header stream gets completed. What was the latency? What was the status code? And we would pipe in this information to the access log to make sense of what was the actual latency of the request. How much time did we spend in x.z? How much time did we spend in xproc? That kind of stuff. So what really happened? We had a very bad logging crisis. So we had exponential growth. Log volume was doubling every 6 months. We had storage cost getting out of control. We had a very high infrastructure impact because 40% of the infrastructure budget was just getting spent on logging. Back in 2022, we did some extensive benchmarking and we saw roughly like 48-50% throughput degradation just because of logging. And then we had a extensive operational pain. Mean time to resolution for an incident was in hours and not in minutes. We were doing all these logs. There were millions of logs, but we couldn't find the signals that we needed in these logs. Like we must be emitting logs on the data plane, but they were getting sampled. We were not able to tie it up on the control plane, and there were a lot of things happening. This is a very high level graph on what happens when you start sampling, like how it impacts the throughput. So if we don't do anything, if we just write everything, we notice that we would only serve, say, 800 QPS per vCPU. And if we start sampling everything, like just remove the access logs, then we went up to 1800 QPS, so roughly like 2.5x. And then, yeah, there were some benchmarks that we did at 20%, 40%, but then roughly there was a huge impact, like if we start sampling the logs versus logging everything. I wouldn't go too much into the benchmarks. They were very specific to a very specific workload. And then we run envoys in Kubernetes, so the environment was different. But yeah, these are the three high-level problems that we saw. We started seeing drops in our throughput as we added more and more logging fields. Like we started with the 5 fields access log, and then we had to like add more fields. We grew it up to 45, 50 fields that we were logging per request. Our logging systems got overwhelmed and they started rate limiting and dropping logs randomly. So there were cases when we got an incident, we would go back and we would check the logs and we would realize that log was not there. It got sampled or it got dropped. Logging became super expensive for us, both the cost to emit the logs and also to process and store these logs. So just to dive deep into a little bit why we need these access logs, like can we just sample everything? Today we use access logs for compliance and auditing. We have various regulatory requirements, auditing, data lineage and access tracking. We use it for security and fraud detection. We also use it for operational visibility, like what happens with an incident and debugging, performance analysis, capacity planning. And I think the most important thing for us is customer support. If we get a ticket, then we need these logs to understand what happened to the request. Today, we have access logs at different layers. We do listener level logging for protocols like Kafka and Postgres. We do TCP proxy, and then we have HTTP layer logging as well. For us, we can't simply turn off the access logs to improve the performance and save cost. They are critical for many things that we mentioned. So I would like to see or tell some of the ways that we discovered in which we can keep the access logs, but then we can balance out the performance impact and the cost. So one of the things that we noticed is the access log extractors. Sometimes the simple direct accessors are not enough for us to capture all the use cases. For example, if I'm using x.z or if I'm using xproc, the filter is emitting the state in dynamic metadata, and I have to use these dynamic metadata extractor, for example, to get the latency information and then pipe it to the log. Envoy provide a lot of different extractors. We have header extractor where you can use request or response and you can pass in the header and you can log the value of that header. We have metadata. We also have cell expression based extractor for advanced use cases in which if you want to use a substring of a dynamic metadata or a request header, you can write a cell expression. The key insight from the micro benchmarks that we did was that not all extractors are the same. So here is a rough comparison of the extractor cost. Like if you look at the direct accessor, it roughly takes 270 nanosecond to extract the field versus if you go to header extractor, they start taking twice the time the direct accessor would take. If we move on to time formatters or metadata, it becomes very expensive, like almost 6 times what you would pay for direct access. Cell is the most expensive. We see up to 28 times the cost that you would spend for direct access. So one of the things we did was there are cases where we would be able to use the header extractor instead of cell extractor or metadata extractor, but then we were just like blindly using cell. So we audited and we corrected those fields in the access log to use headers or metadata and not use cell everywhere. So this benchmarking helped with understanding what is the cost per extractor. This is a only for illustration purposes. Let's assume if you have one cell field and it's taking 7600 nanosecond, and if you have 10,000 requests per second coming in, you would spend roughly 76 millisecond in the CPU, which is like 7.6% of a CPU core. Now, if I take this and apply it to a 10 field format where I have 10 fields in the access logs, roughly if I use different type of extractors, if I use direct, header, metadata, and the cost, the total cost is 3,800 nanosecond. For a 10,000 requests per second traffic, I would roughly spend say 38 millisecond, which is 3.8%. And in production, if I do 45 fields, which has cell and a lot of other extractors, and if my cost per log is 17,000 nanosecond, I'm spending roughly 17% in CPU to just log. And if I multiply this with 100 instances, I'm burning 17 CPU cores only for logging. This is a sample access log that we have today, just for the illustration purposes. We have some direct accessors like connection termination details. We have some filter state coming in from xproc, request headers, dynamic metadata. This is, in this case, the cell is missing, but yeah, we do have some cases where we are also using cell expressions. Now let's talk a little bit about logging filters and how they can help us save cost and also reduce the footprint. Envoy does provide a lot of access log filters. For example, we have response flag filters, we have status code filter, metadata filter, header filter. They're very powerful. They make us, or they help us make a decision on whether we need to log an incoming request or not. They can be combined using special filters like we have and or filters. One of the key insights that we had with the micro benchmarking was that filters are very inexpensive. So just to get a brief idea, if I take a status code comparison filter and I start running it on every incoming request, I spend roughly 3.5 nanosecond. Versus if I go back to the log where we had say 10 or 12 fields, if I aggregate all the access fields that I'm logging, direct access, header, and if that cost comes to 2,000 nanosecond, that's like 1:600 ROI of choosing whether to log something or not versus logging everything. So now look at some of the examples of how we can use logging filters. In this case, I have an OR filter at the very top. So when a request comes in, it will try to go to the status code filter. Here we'll make a decision if it's a 401 or 503 error, it would get logged. If not, then we'll fall back to the second filter. This filter is to record any zeros. For example, if the client ends the request before the server could complete, Envoy would record a status code 0. We thought it's interesting use case for us to capture what really happened. So we had the second layer of status code filter. The third one we had is a duration filter, in which we were interested in the latency of the request. We said if any request is taking more than 1500 milliseconds, we want to know what happened. So we started installing this third filter. And then finally, the last filter is the runtime filter, in which we are making a sampling decision. We want to sample at 10% rate. So for any incoming request, we would go through all the filters. And if none of the three top filters get activated, we would just start sampling at a 10% rate. Now, for the recommendation, this is a 3-tier strategy which we would recommend. You have a first tier where you have essentials, which is always on for 100% of the traffic. You have some very fast fields like status, duration, bytes, path, method. The cost is, say, like roughly 1500 nanosecond. You can use it for basics and compliance. You have tier 2 where you only start logging the errors. So say roughly 5% of the traffic is running into errors, 503s or 404s, whatever you're interested in. You have slightly more fields. You have response flags, upstream details, request IDs. Cost is slightly higher, 2500 nanosecond. You can use it for full error context. And then there is a third tier, which you only use for deep diagnostics. You have, say, 10% of the traffic sampled. You have extensive logging with cell expressions, metadata. The cost is higher, 4,000 nanosecond. So these are the use cases in which you would try to look at the latencies and you would try to like do some deep diagnostics on why the requests are taking that much. Any kind of advanced monitoring, you can use the deep diagnostics or 10% sampling tier. This is the impact that we saw. We saw almost 65% of reduction when we started doing these things, when we started adding, when we started converting our cell-based or more expensive access log extractors to the basic ones. And then we started filtering a lot of logs. We saw like roughly 400K annual savings in just the compute alone. We also saw huge throughput improvements. We improved from 800 QPS per vCPU to 1800 QPS per vCPU. I think that's it for the prepared content of my talk. I'm happy to take any questions.
Thank you, Rohit. We have one question. Do you use OpenTelemetry for log collection?
We don't today.
Okay, that's it.
Thank you.